So we'll do a couple of limit examples, both for 2D functions and 3D functions right now, just to kind of see how to use these. I'm going to take the limit of the function of 3 variables. Actually, I'll stick with a function of 2 variables for now. All of these laws apply for functions of 3 variables as well. Going from as xy versus the point 0, 1, the function x minus xy plus 3 over x squared times y plus 5xy minus y cubed. So we can use the quotient limit law and then the sum limit law on each individual numerator and denominator. The quotient limit law says that this is going to be the limit of the numerator divided by the limit of the denominator provided that the denominator limit is non-zero. And then you can use the sum limit law. I'm not going to keep writing this limit, but you do the sum limit law to get each one of these individual limits. And essentially this ends up reducing down to then just being 0. The limit as xy goes to 0, 1 of x is 0 minus 0 times 1 plus 3 divided by zero squared times 1. You have x squared times y plus 5 times 0 times 1 minus y cubed, which is just 1 cubed. This entire thing then is going to be 3 divided by -1 or -3. And sure enough, that's the value of the limit of this function. So this function approaches -3 as you go to the point 0, 1. This is just a straightforward, quick application of how we can kind of show this limiting process. So we'll do another example. We'll do the limit as x comma y goes to the point 3 comma -4 of square root of x squared plus y squared. This is going to be the same thing as, we can use the root limit law first. This will be the limit as xy goes to 3 comma -4 of x squared plus y squared, all to the 1/2. This is applying the root limit law, and then you have the sum limit law and the power limit law you can apply. And what happens is this is exactly the same thing as 3 squared plus -4 squared to the 1/2, or the square root of 9 plus 16, which is the square root of 25, or 5. So these are two relatively straightforward examples of applying these limit laws. Now, there are certainly other, more complicated scenarios that could definitely arise. For instance, you may have to do some form of algebraic simplification, or other type of simplification, trigonometric simplification, before you can directly apply the limit laws. I'll give you a very good example of this in the next example. So we'll do. Consider the example, the limit as xy goes to 0, 0, x squared minus xy over the square root of x minus the square root of y. You can't directly apply those limit laws to this, because if you try and do this, the denominator here is 0. And the numerator is also 0, so this is, again, it's an indeterminate form, which might make you think that this limit does not exist. But it turns out that would actually be wrong. This limit does exist. There's a way that we can algebraically simplify it and make it look nice. It's, in some sense, it's very similar to the concept of a removable singularity from Calculus 1. So you can use algebra to kind of simplify this. And the way that we do that is by cleverly kind of getting rid of these square roots in the denominator, and noticing that this kind of factors nicely. Specifically, right, if we multiply by the reciprocal, square root of x plus the square root of y over square root of x plus the square root of y. Okay, this is not changing our function at all. This is the same thing as multiplying by 1. So we're not changing the limit that we're calculating here. We're still this limit is still the same limit that we're trying to calculate, L. But doing this ends up simplifying this a lot. We get the limit as xy goes to the point 0, 0. X squared minus xy is the same thing as x times x minus y. It's still divided by square root of x minus the square root of y. And then now we have the square root of x plus the square root of y up here in the numerator, and square root of x plus the square root of y down here in the denominator. So it looks like it's more complicated, but we'll see that this simplifies very, very nicely. You have x times x minus y still, square root of x plus square root of y. When we FOIL this out, do the multiplication out in the denominator, this is going to become this times this, which is just x. And the middle terms cancel. And when you do the last multiplication here, you have to do this negative square root of y times square root of y gives you negative y right here. And notice that what this gives us is exactly a very, very nice cancellation. We get that x minus y divided by x minus y is 1. So the limit that we were originally looking for, remember this is just the limit that we were originally looking for, was the limit as xy goes to 0, 0 of x squared minus xy over square root of x minus square root of y. This is the same thing as the limit of x times the square root of x plus the square root of y, which is just equal to, from our limit laws, now we can apply the product limit law, and then the sum limit law, and then the power limit, or the root limit law, to get that this is going to be the same thing as 0 times 0 plus 0, or 0. So we've effectively determined that the limit of this function is in fact equal to 0. So you definitely want to be careful of things like this, right? Sometimes, even though it looks like the limit may not exist, you can go through and show that the limit does exist, even if you think that it may not exist. It's very, very important to look at things like this. And let's take a second to kind of plot this out and verify that this does in fact make sense for this function. So here is a plot of this function, and we can see very clearly that at 0 the limit does exist, or 0, 0 the limit does exist, and not only that, but at 0, 0 the limit is equal to 0, just like we calculated. And if we kind of move around this function to kind of get a picture of like both the level curves and also the density plot down here of how the function is behaving, we can see very clearly that the domain of this function, right, we have to remove all points y equals x, because that would make the denominator 0. And even though this point right here is not in the domain of the function, so 0, 0 is not in the domain of this function, the limit at 0, 0 still exists for this function from points inside the domain. So this is a really cool example. This is a very good example. So just because you have an indeterminate form, it doesn't mean that the limit does not exist. Right? There are other things in many other types of examples that you could possibly consider and see as well. But the idea here is that this is a very, very good example. Another technique that's very, very useful is what's called synthetic division. Right, so factoring, synthetic division. There are so many different useful kind of algebraic techniques that we can use to possibly simplify functions if we have to. And simplify the calculation of limits if we have to. But sometimes it's important to do that. Whenever you get an indeterminate form like that, the limit may actually exist if you can simplify that both either the numerator or the denominator. So let's do an example of synthetic division, just to kind of show that there are multiple different techniques here that you can kind of apply. But you really want to become remember some of your techniques from algebra and from specifically a Calculus 1 class that were very useful. So let's do, say, the limit as xy goes to 0, 0 of x cubed minus xy squared plus y x squared minus y cubed over x plus y. Again, this, if you just directly try and plug in, you get 0 over 0, which is an indeterminate form. So you might think this limit doesn't exist. But it turns out that we can use a method from algebra called synthetic division, or division of polynomials, to simplify this. This is like long division of polynomials. So if you remember how to do long division, hopefully, from either a pre-calculus course or from an arithmetic course, we can do this with polynomials. Specifically, if you have dividing by the polynomial x plus y, and we're dividing the polynomial x cubed plus y times x squared minus y squared times x minus y cubed. And this works out exactly like normal division does for normal, you can say real numbers. But now what we're doing is we're saying kind of treating the powers of x as our individual placeholders for coefficients. So specifically this function right here goes into this polynomial x squared times. I'm trying to get rid of the highest order terms in x here. So specifically, if I multiply x squared by this polynomial and subtract, I end up getting x squared times x is x cubed. Then x squared times y is y times x squared. So the remainder for this first division is actually pretty nice. It ends up giving us x cubed minus x cubed cancels out. Y times x squared also cancel out. And what we're left with for the remainder is just negative y squared x minus y cubed. So again, we want to do the next highest order. So we got to figure out what we have to multiply this by to get rid of this x term right here. So this negative y squared x. That's going to be exactly multiplying by this negative y squared. Because when I multiply by negative y squared, I get negative y squared times x. And then also what's nice is that I get negative y squared times y is negative y cubed. So when I subtract out this, the result after doing this division, these two terms cancel out and these two terms cancel out, which actually give us a remainder of 0. Which means that this polynomial right here is really, it's the same thing as the following. It's the same thing as, so what we've just shown is that the polynomial x plus y divides into the polynomial x cubed minus xy squared plus yx squared minus y cubed evenly. Specifically, this numerator is equal to x plus y times x squared minus y squared with a remainder of 0. Which allows us to simplify this, as x plus y divided by x plus y is 1. The limit of this limit as we go to 0, 0 is the same thing as the limit x squared minus y squared as we go to 0, 0, which is just from our limit laws, 0 minus 0, which is equal to 0. So this is an example showing how you can use synthetic division and really any other algebraic technique that might be useful to use our limit laws and figure out the limits of specific functions. And I just realized that this example that I just did is, I keep saying synthetic division. This is actually an example of what's called long division, so polynomial long division. Synthetic division is a more simplified method of long division, but I typically like showing the long division because it's less time to explain what exactly I'm doing. But the point is that all of these algebraic techniques are super useful for evaluating the limits of algebraic functions and rational functions as well of multiple variables. So here we see a level curve and density plot of this function. And we can clearly see what we predicted, which is that as we approach the origin, 0, 0, the limit of this function is in fact equal to 0. Even though the point 0, 0 is not included in the domain of this function. It's not included in the domain of this function because the entire line y equals negative x is not included in the domain of this function because this makes the denominator equal to 0. So this is very cool. And if we go through and kind of rotate this a little bit to kind of see this surface, what this surface looks like. So this is the surface right here. We see very clearly that the surface is a type of hyperbolic paraboloid, just like the equation x squared minus y squared. But this is a hyperbolic paraboloid that's all the points y equals negative x are not included in the domain. And the function itself is more complicated. It's this cubic polynomial divided by this linear polynomial. Nevertheless, the shape of the graph looks like a hyperbolic paraboloid, which is a general, one of our general quadratic surfaces. So this is very, very neat and I think very illustrative, both for verifying our limit calculation and also for showing you that even if you take a fraction of polynomials, they're going to behave just like you would expect for the shape of the functions. This is a very, very, very nice and kind of powerful method. You can see that all these limit laws are very powerful. They allow you to, if you can simplify your function and down to a point where you can apply the limit laws, you can very easily go through and get the value of a limit. So the last thing we're going to talk about today is the definition of continuity, or a continuous function. And what's nice is that once you're okay with taking the limit, and whether a limit exists or doesn't exist, the definition of continuity follows directly from the definition of a limit. Specifically, we say that a multivariable function is continuous at a point x naught if its limit exists at the point that's the first thing that has to be true, and we have to also have that the value of the function is equal to the limit at the point. So notationally speaking, for a general function, you say that the limit as x goes to x naught of f of x is equal to the value of f at x naught. In 2D, this is the same thing as saying the limit as xy goes to the point x naught, y naught of f of xy is equal to f of x naught, y naught, or say, in 3D the notation is similar. You say that the limit as xyz goes to x naught, y naught, z naught of f of xyz. This is equal to f of x naught, y naught, z naught. So it comes directly from the concept of the limit that we're talking about. So we say that a function is continuous if the limit exists at that point and then also the value of the function is identical to the value of the limit. It's really the same sort of idea as in single variable calculus, and it depends directly on this definition of the limit and the idea of the limit. So this is a very, very nice concept, and it turns out that we have a final kind of general property that's very, very nice for the composition of continuous functions, and we'll use this a lot as we kind of going forward. So first I want to kind of talk about what a composition is for a multivariable function. So say that the composition of multivariable functions is just like composition for multivariable functions of a single variable. It's a little bit more complicated. So let's say, for instance, we have some function, we'll call it w is equal to f of xy, but then you also have that x is equal to some function g of uv, and y is also equal to some function h of uv. You can say that w is then also equal to a function of u and v. Specifically, it's the function when you plug in g of uv for x and h of uv for y. So for example, let's just take a specific example. You could say, let's say f of xy is the function x squared minus y squared, and then maybe x is equal to, say, uv, u times v, and y is equal to e to the u times v. Or we'll do e to the u plus v, just to make it a little bit different. So if w is equal to f of xy, then w, the composition as a function of u and v, is going to be uv squared minus y squared, which is e to the u plus v. And so this is how w squared. This is how w depends on u and v in this compositional relationship. Right, so in general, one of the things that you wanna use when you're dealing with compositions of multivariable functions like this is what's called the tree of dependence. Also sometimes called the chain of dependence. And this just kind of gives you an idea of how everything depends on everything else. So if you say have that w is equal to a function of x and y, w is the top of the tree. It then depends on x and on y. And then if x and y themselves are both functions of u and v, so x is some g of uv, and y is some h of uv, that means that x depends on u and on v, and y also depends on u and on v. So this is the tree or chain of dependence for this composition. But this is going to be a very, very big thing for us, especially when we go through and talk about what's called the multivariable chain rule. So this is just what it looks like for a function of two variables, but you can kind of extrapolate this and see that you can also do this for functions of three variables or any more variables. which is a very, very useful thing to consider. So the main property here that we have is that if we have a continuous function, or a composition of continuous functions, so let's say f, g, and h are continuous, if you take, say, the limit, this is the final property that we have for limits it's really limits of continuous functions. I should say the final computational property that we have. If you take the limit of a composition like this, as say uv goes to u0 v0, this is the composition f of g of uv h of uv. If these functions are all continuous functions, so the limit of all the functions exists, so f is continuous, g is continuous, and h is continuous, this is the same thing as f of the limit of as uv goes to u0 v0. So it's the same thing as f of the limit of g, and then the limit of h. Which, if g and h are both continuous functions as well, this is the same thing as f of g of u0 v0 h of u0 v0. So if you have a composition of continuous functions, you can take the limit and actually bring the limit inside as you take the limit. So this is a very, very useful computational property that we see a lot, and we're going to use a lot when we're going through and evaluating limits. And what we'll end the lecture on is going to be this last, so that we have one more property. This is called the extreme value theorem. This is for continuous functions. And this says the following. It says that if f is continuous, on some closed bounded domain, then it attains absolute maximum value on the domain. We'll say absolute maximum and minimum on the domain. And this is the last big property that we will see in many different examples as we kind of go throughout the course. So you can use the ideas that we've been talking about to prove this, but the idea is that this will be an important theorem when we start talking about optimization of multivariable functions and maximizing and minimizing multivariable functions. So to demonstrate an example of this theorem, what I'm going to do is I'm going to use one of my favorite functions which is the function x times y times e to the negative x squared plus y squared. And this is one of my favorite functions in multivariable calculus for a number of different reasons, but the main reason for us right now is that it's a perfect example of a function that for any closed boundary, so closed and bounded domain, it's clear that it attains an absolute maximum and minimum. So what I'll do is just pick the simplest possible domain that I can kind of consider, which will be a circle. And we'll just look at a plot of this function and see where it attains its maximums and minimums. Note that the function's a little bit complicated because you have x times y, which the function x times y has hyperbolic level curves. The level curves of x times y are hyperbolas, and the level curves of e to the negative x squared plus y squared has level curves of circles. So the underlying level curve structure isn't immediately obvious. You can go through and directly show what it's going to be, even without using a plotting program, but I think I just want to show the level curves of this to give you an example of this theorem. So here we see a plot of this function, the function x times y times e to the negative x squared plus y squared. And I plotted it over a rectangular grid. I also, though, drew a circle indicating the domain that we're looking at, possibly optimizing the function over. So kind of take a look here. And this is a plot of what the surface looks like from, well, the z-axis right here. We have negative x, negative y is the contour plot. But if we kind of rotate this, we can see that this is what the function looks like, the graph of the function looks like in three-dimensional space. And we see very clearly that inside the domain of the circle, this is achieving its maximums, so 2 maximums and 2 minimums as well. And they're both occurring inside the domain. But this is not the only thing that could happen. The only way that this could happen, an important theorem that we're going to show a little bit later on, and we're going to use when we optimize functions, is going to be that the maximum of a function on a closed bounded domain will always occur either in the interior like this or on the boundary. So let's consider a slightly smaller domain, and we'll kind of center it around one of these maximum points, and we'll see an example of this. But both of the examples are good examples of the previous theorem, which is that continuous function on a closed bounded region will always attain its maximum and minimum values. So this right here is a plot where I've considered a smaller domain, a circle of radius 1 instead of radius 2, and I've kind of shifted it to the location of the max that we found before. And even for this function right here on this domain, we see very clearly that it attains global maximum on the inside, so maximum value on the inside of the domain, and global minimum value on this domain actually on the boundary here and the boundary here. So this is one of the big things that we see in general, and it's good evidence of the previous theorem that I wrote down. And this is something that's going to be really, really important a little bit later on when we define global maximum and global minimum and we start optimizing multivariable functions. Because this, in some sense, is at the heart of many of the modern important applications of multivariable calculus to the real world. And for my last example of this theorem, I'm going to show that the theorem holds, give an example of how the theorem holds in 3D as well, and really for any number of dimensions. This is for, say, a function of 3 variables, and we'll make it as similar as possible to the previous example. The the density plot in 3D is going to look very similar as well. So this is going to be for the function x times y times z times e to the negative x squared plus y squared plus z squared. And we'll open up a Python plot of the density plot of this function along with some cuts of the level surfaces to really show you that this is attaining its maximums and minimums in really any domain that you want to consider. So this is a visualization of this function, and sure enough, we can rotate it around, and it appears from the level surfaces that this function has 4 minimums, 4 maximums. And it turns out that each one of these values has the same, height, the same value in the along the output, and it's in some ways very, very closely to the previous 2D example. But what we can do is kind of show traces, and along these traces, we just the color is the value of the function, and you can very clearly see the appearance of these maximum and minimum in 3D for a 3D function. Sure enough, if you want to kind of do this in any given direction, you can go ahead and do that. Same thing down here. So we're seeing that we can really use this idea of traces to, along with level curves and level surfaces, to tell us about even functions that may be very hard to visualize. For instance, in this case, a function of 3 variables whose graph we can't directly see because the graph lives in 4-dimensional space. But nevertheless, this theorem is satisfied. Right? This is a closed bounded region. That's the cube in 3D from -2 to 2 in every coordinate direction. And the function clearly attains its maximum and minimum values here. Because as we move away, it's going to be decreasing exponentially in every given direction. So I hope this was a very illustrative lecture. I hope you learned something, and I hope you had a great day. But this is going to be it for the lecture. Thank you very much for listening, and I'll see you in the next one.